When people ask me if AI is indeed everywhere, I like to point out a recent commercial I heard about an AI powered toothbrush. Now, I fully expect the AI powered toothbrush to work just as well in Chicago as it does in Cincinnati, as it does in Cairo. However, would it surprise you to know that not all AI algorithms perform equally well everywhere? This is where the concept of federated learning comes in. Hi, I'm Tony Reyna. I'm the Chief AI Architect for Health and Life Sciences at Intel. In this series of videos, we're going to be talking about federated learning, which is a privacy preserving way of training AI algorithms. Federated learning allows you to move the model to the data rather than moving the data to the model. And this makes it very useful in cases where you have sensitive data that can't be easily shared. Our goal in this series of videos is to show you how Intel is allowing data scientists to perform federated learning and how Intel technology can help to secure federated learning in ways never seen before. My goal personally is to allow data scientists to train models on diverse, unbiased, large data sets from all over the world so that the model that they create and works well in Manhattan works equally well in Mumbai and Moscow and Montevideo. I hope you'll join us in this adventure. So, in the last few years, artificial intelligence has moved from research to production. What you're looking at here is a convolutional neural network that we use at Intel to create better hardware and software for AI researchers. This model takes as input an MRI scan, and our customers have created dozens of similar models that are already on the market today and have been cleared by the FDA to help with patient care and treatment. But the problem we come up against is that these models are trained with data, and access to large, diverse, multinational data sets for training these AI models is actually quite limited. In fact, this recent review in Scientific American showed that about 70% of the AI models in published studies that they reviewed relied on healthcare data from just these three states: New York, Massachusetts, and California. Now, that's not really what I would consider very diverse. I usually use the phrase, the model has to perform as well in Manhattan as it does in Madrid, Moscow, Montevideo, and Mumbai. The problem is that there's plenty of data being generated every single day, but it's often siloed. And this is not just healthcare data, but it's any data with an expectation of privacy or security. Financial data, government records, personally identifiable information. And it's not just that regulations such as HIPAA or GDPR prevent that data from being used, but it's also that the data is too valuable. Remember, data is the new oil, as they say, or it's too large for data owners to safely or efficiently move that data around and train AI models on some centralized server. Google came across this problem when they wanted to train AI models for their Pixel cell phones. And so they started with a model that could predict the next word a user would type in an instant message on the cell phone. Now, it wouldn't be very private if they sent their users' personal IMs to a centralized Google server for training just this new model. So Google turned the problem on its head. Instead of moving the data to the model, they moved the model to the data. Every night, a copy of the global model is sent to the user's cell phones, and that model gets trained locally on the user's phone without actually exposing the data back to Google. Only the updated model is sent back to Google, never the IMs. This allows them to continually retrain on real-world data without exposing the data itself to Google or anyone else for that matter. And Google called this federated learning. Intel was the first to show that this same technique of federated learning would work in medical imaging. In this study I'm showing, which is actually a follow-up to our initial 2018 paper, We demonstrated that the brain tumor model I showed you before could be trained using federated learning by sending the model to the individual hospitals rather than sending the data to Intel. Our results show that the FL approach could attain a model that was more than 99% of the accuracy as if the model were trained centrally. We've open sourced this base code for federated learning in a project called Open Federated Learning, or OpenFL. OpenFL is a great way to get acquainted with federated learning and allows you to run your own experiments. We hope you'll stop by our GitHub repository today and check it out. Please give our repository a star if you like what we're doing. Spasiba. I talked about how artificial intelligence is helping to create models that are being used to diagnose and treat patients today. But I also talked about the issue with getting access to large, diverse data sets. And I explained how federated learning was a way to train AI models on these really large, multinational, potentially sensitive data sets in a way that maintains privacy. I want to take just a few minutes to give you an idea of exactly how federated learning works, and I call it showing you how the bits move. So this gobbledygook here is a convolutional neural network model that we call 3D-UNet, and it looks really difficult to understand, but I'm going to try to simplify it for you. So all we're doing is we're taking in an MRI, which is just an image, in this case of the brain, and what we're trying to do is find just where the brain tumor is. And the way we do this is we've actually had expert radiologists that have colored in where the brain tumor is. And so I always think of this as, imagine you're back in elementary school and your teacher asks you, here's a coloring book, and I want you to use the red crayon to color all of the cats, and the blue crayon to color all the dogs, and with the green crayon, could you please color in all the glioma tumors? The radiologist is actually able to do all three of these things, and we're actually just using this equation, which doesn't look like an equation, but I'll show you in a second, to filter out everything except for the tumor. And so if you boil it down really simplistically, and I am being quite simplistic here, a neural network boils down to this equation. And there are some nonlinearities here. There are some ReLUs. There are some things that you don't need to concern yourself with. But it's basically just for this given pixel, what's the probability that that part of the image is a tumor or not? And ultimately, it ends up being, let's say the model has 20 million numbers that you're trying to find. So it's really just finding these 20 million numbers that you can adjust and will allow you to filter out just the tumor from the MRI. Now, federated learning, as I said, turns the usual model on its head. The usual model is you take all the data, so all of these MRIs and all of these radiological scans, the actual annotations, the coloring book, if you will, dumps it into one large server and trains a model on that. Instead, with federated learning, or FL, what we'll do is in step one, we'll have something we call a parameter server, and we'll take a global model. It could be just a random model, so these are our 20 million weights, and we're going to move our 20 million weights of our model to the institution A, B, and C. Let's say this is hospital A, hospital B, hospital C. And institution A, B, and C is going to use deep learning. It's something called stochastic gradient descent. It's basically going to wiggle those numbers, try to find the right set of numbers that seem to filter out for institution A's data, for hospital A's data. Hospital B will have the same thing, and hospital C will have the same thing. And so these 20 million numbers, one set from A, one set from B, one set from C, are sent from these in step two, what we call collaborators, these individual hospitals with the data, to step three, an aggregator. And the aggregator is where we put all three of these updates together into one consensus model, one global model, and we rinse and repeat. We send that model back to step one, and we send the new global model back to these institutions for more training. And we can continue these rounds over and over again for as many rounds as that we want until the model is trained. So concretely what this looks like, in this case we're using the standard model, which is called Federated Averaging. That's what's happening at this aggregation step using this aggregation method. I've got these numbers, 20 million of them. I've got one set of numbers in blue from hospital A, one set of numbers in green from hospital B, one set of numbers in red from hospital C, and I'm actually just going to average them together. In this case, I weighted them all equally, so it's just this plus this plus this divided by 3. I could weight them, and in fact, that's what federated averaging does, is it gives a higher weight. Let's say hospital A contributed half of all the data, it would actually get half the weight. If hospital B contributed a tenth of the data, it would get a tenth of the weight. So it's just a weighted average of each individual number that's being sent back from the model. And as I said before, we were able to show that for these sorts of models that are doing brain tumor segmentation, the model actually converges really nicely, meaning that it achieves about the same level of accuracy as if you had all the data in one place. In our cases, this is an experiment where we actually do have access to all of this data. It's actually publicly available data. And what we did is we trained the model in this curve based off of centralized training. So we just dumped the data into one big server and we trained it. That's the standard way of doing it. And then we actually knew what the original hospitals were. So we actually did the federated based on just each hospital's data, training independently and doing this federated technique. And you can see that it took a little bit longer, a few more, in this case, an epoch was around. It took a few more rounds to actually get there, but eventually it was able to reach the same level of accuracy. We also tried two other methods. If you think about it, there are many different ways of doing this if you want to train locally and try to put things together. So in these two methods, which we're calling incremental learning, this is just our word for it, we were actually taking a model and moving it from hospital A, training it locally, taking that model, the trained model, moving it to hospital B, training that locally, taking it to hospital C, training that locally, and then in a cyclical manner, maybe we come back to hospital A or B or one of the other ones and just keep looping back around as many times as we want. Those two actually didn't do as well, and you can actually see where there were places in this case, and actually over here as well, where there's something called catastrophic forgetting. And what happens is that if I'm moving and training it completely at hospital A and then moving completely at hospital B, if hospital A, let's say, has all children at the hospital, it's a pediatric hospital, and hospital B has geriatrics, so it has people that are, let's say, 65 and older, it might actually lose information about how to correctly diagnose children. So it's called catastrophic forgetting. It'll eventually pick it back up again once it gets back to hospital A, but there's this danger. The bigger danger that we see is the following. So if you followed what I said before, which seems pretty easy for this federated averaging, is I've got hospital A gives me these numbers, 20 million, hospital B gives me these numbers, C, and so forth. But what if hospital B, for let's say the second weight, W2, gives me 1, 2, 3, 4, 5, and all of the other hospitals are giving me things like 13, 12. Is this real? Is this an error? Is this an attack? If you think about it, if I'm doing an average here, 1, 2, 3, 4 is going to really pull away from, if we assume that these are giving me real numbers, this should be somewhere between 12 and 13. And now I'm being pulled into 1, 2, 3, 4, 5, which could completely cause the model to collapse. We call it poisoning the model. So there's some ways called robust aggregation that will help in this. And obviously, there are things that'll handle outliers. You can do things like medians, harmonic means, something called Olympic scoring, which, if you think about the Olympics, they have the same issue, right? What if one judge says it's a 10 and the other judge says it's a 2, and all the other judges say, nah, it's a 7. You throw out the 10 and you throw out the 2. You throw out the top and the bottom score, and you actually just do the average of the remaining scores. So that's Olympic scoring. All of these are fairly good at handling outliers. There are also more complex methods. I talked about federated averaging. There are things called federated procs, which adds an additional loss term if you understand the concept of loss terms, and it makes it so that you can't move too far away during one round from the previous round's model. There's also something called federated match averaging, which if you know something a little bit more about convolutional neural networks, they have these convolutional filters. And when you think about it, hospital A and hospital B, what they call filter one in layer one could actually be different filters just because of the stochastic nature, the randomness. So in fact, hospital B, filter 5 in layer 1 could look about the same as layer 1, filter 1 in hospital A. And so what federated match averaging does is it first says, let's try to align all of these. And instead of just saying, we're going to average layer 1, filter 1 of everyone, we're going to first find the matched filters, average those together, because if I average this and this blindly, I get something that is nonsense. But if I get this and this, now I've got something that seems to be consistent. You can check out all of these issues and try experiments yourself in using federated averaging, federated procs, and so forth in our open federated learning project, OpenFL. Again, it supports TensorFlow and PyTorch models. It's Apache open source, and would really love it if you went to the website today and gave us a star. Thanks very much. So in the past videos, I've given you an overview of federated learning, and I've talked about this sort of FL workflow. So basically, we've got in step one, some sort of parameter server that's going to send a global AI model to different collaborators, institution A, B, and C. This could be different hospitals or anywhere that the data actually resides. The collaborators will do a local training on their particular data set. And then in step three, they'll actually send a new update for the model back to something we call an aggregator. The aggregator combines all of those models into a single consensus model, a global model, and that gets sent back to the parameter server, and we repeat in what's called a round. Concretely, I talked about federated averaging, which is the typical way that this is done, one of the typical aggregation methods. It's a really pretty simple idea. You can kind of boil down a deep learning algorithm. The topology stays the same, so it's really just passing around weights of the algorithm. So let's say you had 20 million weights for a particular model, for a particular AI model. Maybe it's 5 million weights, maybe it's 2 million weights, whatever it is, you've got a set of X or N number of values that you're sending, in this case 20 million. And after that local collaborator training, I've got a slightly different version of these 20 million numbers from hospital A, B, and C. And in federated averaging, I'm just going to, for every single number, so W0, W1, weight 1, weight 2, weight 3, I'm going to do an average, and specifically a weighted average, and the weight is depending on how much data hospital A is actually contributing. We also talked about, okay, well, that sounds great, but what happens if hospital B, for one or more of its numbers, gives us something that seems way out of whack with the rest of hospitals? So hospital A and C say it's 13 and 12 for this weight number 2, and hospital B says, nah, it's 12,345. Is this real? Is this an error? Is this some sort of an attack? And I talked about, okay, well, we can handle that. We know how to handle outliers in statistics. So one way would be, some sort of aggregation method, some sort of statistic that handles outliers pretty well. Things like medians, harmonic mean, Olympic scoring, where we throw out high and low numbers. There are more complex algorithms, something called FedProcs, Fed match averaging. There's all sorts of interesting algorithms to handle these outliers. But what you find in the literature is by moving these models out to these collaborators, you've now opened up new security threats. And these are security threats that sometimes, in many cases, can actually be addressed. Um, I talked about what happens with the 1, 2, 3, 4. So in something like that, it might be a poisoning attack. It might be someone is actually trying to send you updates that are so far off that no matter what aggregation method you use, you're not able to compensate for it, and the model never trains. So you go through all of this expense in setting up this federation, and you never actually get a model that converges to something that's useful. The literature also shows, and you can find these papers showing that if you take this to the extreme, assume that not everyone is actually playing by the rules. Assume that even though I've sent hospital a model and asked it to train on its local data, instead, it actually creates its own algorithm that tries to attack the federation. Specifically, in some papers that have been published, they use what's called a generative adversarial network, a GAN, and the GAN is actually able to push updates, so that 1, 2, 3, 4, but make it close enough that it's really hard to tell whether it's a real update or not. Maybe they do something that's 22, and it's not too far away from 12 and 13, and you think, okay, well, that's good. And that might be real, and your robust aggregation method lets it through, and it continually, after many rounds, keeps pulling things away. In particular, in those sorts of attacks, you can actually set up the GAN so that the other collaborators end up getting a model that performs so poorly that their updates have to memorize more and more of their own data in the model itself. Remember, the model is the only thing that's being shared, not the data, but the model is learning things about the data. And if it overtrains on the data, it actually learns lots of statistics and lots of information about the underlying data. And in this case, this is from an actual paper where an adversary was able to pull out from the model by doing a model inversion, the original data or close to it, uh, an image that came from another collaborator in the network. So the point is, FL solves a lot of data access problems, right? But it doesn't actually protect the model, number one. So I'm sending the model out. There's no reason that hospital A, hospital B, hospital C, or anybody who gets the model can actually just outright steal the model. They've been sent it, they have it. If this is your intellectual property, if this is something that you want to use for a business, that's something that's probably not desirable. FL doesn't protect the training completely, and it doesn't completely protect the data because of these attacks. We're assuming, we're making the implicit assumption that everybody is following the rules. And if everybody's following the rules, we're okay. But if everybody doesn't follow the rules, which is usually the case in the real world, or at least we expect it to be the case in the real world, that's when things fall apart. So what do we need to actually secure FL? Well, we'd like to have confidentiality. We'd like to have a way of protecting data and models from the risk of exposure to untrusted parties during runtime. I get this all of the time. This is the one part that I think people don't get is they say, I encrypt my models and I send it out in an encrypted form and I'm good. Well, in order to actually use your model, you have to decrypt it at some point, unless you're using something like homomorphic encryption or some other sort of method. There's no way to get around it. You have to decrypt your model, and that's when I'm going to steal it from you. I'm going to wait until you decrypt it, and I'm going to actually get into that memory. I'm going to dump it. I'm going to go spelunking that memory, and I'm going to steal your model right from memory in use. We also would like to have execution integrity. We'd like to protect the computation, the training of the model, from being changed at runtime. What happens if somebody says, I'm going to change one of the libraries that's being used during runtime, and I'm going to put in a backdoor somewhere that allows me to dump something out. So we want to make sure that integrity is maintained. The third thing that we would really like to have is a way of attestation, and that's validating that the software and the hardware are in fact genuine. So it's basically, if I'm asking you to do a calculation, I'm asking you to run a program, and you give me an answer, like 1, 2, 3, 4, 5, you have to have some sort of receipt that says, The only way I could have generated this number 1, 2, 3, 4, 5 is if I actually ran the training script, the algorithm that you asked me to run, and that's Attestation. Conveniently, Intel actually has a solution that addresses these three. And there are other companies that have this. It's something called a trusted execution environment. Intel's version is something called Software Guard Extensions, SGX, and it provides security during execution in hardware. So it's a set of CPU instructions that can be used by applications to set aside private regions of code and data. And specifically what this means is we call this an enclave that gets set up. And an enclave is a piece of hardware, compute and memory, where if you're an attacker and you have access to the operating system, you can't get into my app. If you're on the VM, you can't get into my app. I'm able to actually run a program on your computer, as long as you allow me to do so. I'm able to set up an enclave such that even though it's your computer, I'm the only one that actually has access to this. And so what happens is that it adds in this confidentiality, this integrity, and this attestation piece by using a trusted execution environment. So confidentiality, I'm now able to send you an AI algorithm that I own, but that you're not actually able to see. And so I can protect my IP. I'm able to make sure that you can't change anything and that you can't do anything differently than what I've asked you to do. So I can't have threats that are being generated by you because you can't actually be adaptive to it. So only approved models and training procedures, and we're actually protecting the execution with algorithmic defenses. So things like robust aggregation. This helps prevent attackers from using the model, and it helps prevent attackers from actually breaking the rules. So now if we talk about federated learning, it solves a lot of data access problems. And if you use trusted execution environments, such as Intel SGX, it can protect the model, we can protect the training, and we can protect the data. For more information about this, we actually have public demos. One of them we showed off at the Supercomputing 2020 conference in Atlanta, where we were actually training on the next generation of Intel Xeon servers, codenamed Ice Lake. And Ice Lake servers have Intel SGX that can create enclaves. In this case, I believe they were around 40 gigabytes in size. We had enclaves on two different machines, one running an aggregator, one running a collaborator, and the other machine another collaborator, and training our usual brain tumor segmentation model, all protected by SGX and all doing federated learning. If you want more information, please go to this link to show you more details, show you the demo as it's training. In this video, I'm going to go through the multi-node federation. So this is going to be quite a long video because I want to set things up on two collaborators and one aggregator node. It's kind of the minimal federation. I'm going to take you through the high-level idea and then walk you step by step through the procedure. So buckle up. We will try to get through this. If you want to follow along, you can go to our GitHub page, Intel/OpenFL, and we've got a button here for our docs. There's also a Slack channel if you want to ask questions, or down here is our online documentation. In past videos, you've probably gone through our Jupyter Notebook tutorials, which you'll notice are currently usually just a single node. So I just want to show you a multi-node. And so what we're going to be following through is in the OpenFL documentation. We're going to be doing the Hello Federation, your first federated learning training. And let me do a high-level diagram first, show you the workflow, give you an idea of the steps that we're going to go through. So I broke it down into 5 basic steps. There are 3 nodes here in a basic federation. Nodes 1 and 3 are our collaborators. So I'm going to call it collaborator A and collaborator B. And then node 2 is our aggregator, which is also going to be our model owner,
which in fact I'm also going to make our certificate authority in this case. First step is you want to install OpenFL in a Python virtual environment on all of the machines. So these collaborators are going to be installing this. Now, I want you to think about scaling in this sense as if you remember in a real federation, there are actually going to be people to help you scale. So even though I'm going to be doing all these steps, and it looks like a lot, this is for every individual collaborator who owns their node for them to do. Second step after they install OpenFL is the model owner is going to create what's called an FL workspace, a Federated Learning workspace. This involves a plan, a Federated Learning plan, an FL plan, and then the code that they want to run. I'll show you how to do that, and we've got some great templates to get you started. Once you have this plan and code and you're comfortable with what model you want to use and the data loader and all of that, you then need to transfer that workspace, the plan and the code, over to all of the collaborators in your federation. In this case, I'm just going to be doing it manually, just showing you with SCP to skip it over to securely to those nodes. Obviously, there are lots of ways to transfer work from one node to the other, but I'm just going to take you through a manual step. The fourth step is setting up the certificates. It's expected in a real professional, real world federation that you're going to be using a PKI that has been granted from a approved certificate authority, someone that everyone agrees is to be trusted. Again, this is a one-time thing. We're using this for the mutual TLS connections. And so collaborator A has to have a PKI that's signed by a certificate authority that's everyone agrees on is to be trusted, so that she can present her certificate and say, I'm collaborator A, and this is how to securely connect with me. The same thing with collaborator B, the same thing with the aggregator node. As long as they all have a way of trusting that they have competent certificates, valid certificates, they'll be able to connect, and without that, they won't. So again, I'm going to show you in the OpenFL code, we do have a way of setting up a certificate authority. It's designed for just testing, for making sure things work, for simulations if you'd like. But in the real world, it's expected that you're using a professionally generated certificate and signed certificate. Again, you're also going to have data files on each of the collaborator nodes. And so once everybody has these kind of first four steps done, which again, everyone's going to be doing themselves, I'll be showing you and doing all the work. So that's why it takes a little longer. But this is really a one-time thing that they end up doing. And then they're just going to start the nodes. So they're going to start the Federated Learning code that's on each node, and that's going to read the plan and start going through the code that was sent over according to what the plan specifies. So let's look at the setup here. What I did is I have three different consoles open up. And so these windows are showing three different machines, three different nodes, three different computers. I am going to show you on the, this one's the aggregator, and these two I'm calling the collaborators. On the aggregator, I'm going to show you how to set up OpenFL, and I've got it set up on the other two. And so I've got a Conda environment, and I need to create a new virtual environment. Conda create. I'm just going to call it OpenFL env. Create. You can call it whatever you'd like. Pip and Python 3.8 in the environment, and it'll create this environment for me. And now my environment is created, so I can activate OpenFL env environment, and now I'm in that environment. From here, I can just do pip install OpenFL, and it'll pick up OpenFL from PyPy and install it. So it'll take a second to install. And once it installs here, we should have the fx command. We go back to here. step one, make sure you've initialized the virtual environment and can run the command fx. So virtual environment is installed and OpenFL is installed. And if we do fx minus help, or just fx, make this bigger. So this is now a new command that is available to you in this environment that OpenFL provides. And this is our command line interface. So everything that I'm going to show you starts with the command fx. And then it's a noun and a verb. So collaborator certify or collaborator start. Things to do with the tutorials. These are the Jupyter notebooks. Things you can do with the plan. Things you can do to the workspace. Things you can do with the aggregator, and so forth. So everything's going to be a command starting with fx. Okay, so I've got step one done. Step two, for this, I'm going to do a demo where I'm going to be starting with one of our templates. Templates are end-to-end federated training demos, so they should be a good sanity check to make sure that things are actually working. And then templates also allow you to build on that template and maybe change it with your own model or your own data loader. And I'll give you an idea of how to do that. We've got a bunch of different templates here, and we keep adding to these. These are, again, full demos. So I'm going to be using just the MNIST. This is our Hello World one. I'm going to be using the Keras one. There's also a Torch one down here that you can try as well. These are just simple convolutional neural network, a few layers, and then predicting the MNIST data set. Okay, so in the instructions we have setting up these variables just to make it easier. I won't do that here. I'll just show you the actual command because it's just as easy. So on the aggregator, I'm going to create a workspace. So right now I've got just a few files here. Workspace create, and I'm going to say in my home directory, I want to have a subdirectory called my federation, and I want to use template, and it is just Keras CNN MNIST, Keras CNN MNIST. So Keras CNN MNIST is the template. I hit enter, and now it's creating the workspace directories, the workspace templates. The template has a requirements.txt file, so it knows what it needs to run, and it tries to install those in this Python virtual environment. So that's why it's useful to have the virtual environment, because it's going to be installing its dependencies. So it just created a workspace called My Federation. If we look, we'll now find a My Federation directory. And in that directory, there's a certificate directory for our PKI. There's a save directory that holds the weights of the model that are being passed from the aggregator to the collaborator and back. There's a logs directory. The data directory is on the collaborators. That's where you would symbolically link your data. Requirements file, if you have, if you want Pillow or NiBabble or any sort of third-party package that needs to be installed for your specific workload. A plan file, which we've talked about before. The plan is just a YAML file, actually a collection of YAML files that it says these are the network settings, these are what the collaborators do, this is what the aggregator does, these are basically the rules of the federation and the settings of the federation. And then this code directory. Let me just show you the cert directory first. There's nothing there. The save directory, there's nothing there. The code directory has, because of the template, has a Keras CNN. So take a look at that. And so if I go through this, it should seem pretty familiar to you. We are using a Keras task runner, which is something OpenFL uses. And we have a function called within that class called build model. And in build model, this should look familiar, Keras code to define a Keras model and return that Keras model. So if you want to change it to your own model, you can add that code right here. Again, this is a really simple model, just two 2D convolutions, flatten it, do a couple dense layers, and out to a softmax, and we're all done. The other thing is the data loader. In this case, it's since we're using MNIST, and MNIST is basically downloaded from the internet and is basically, you know, the hello world. What we do is we don't actually save the files. We have it all in memory. And so usually with your data loader, you're going to point it toward the path of the data. When I do this demo, the path I'm going to actually pass in is just a number like 0, 1. And I've set up the data loader that it just takes that data path and actually says you're using shard 1 or shard 0 or shard 2 of the MNIST data set that's in memory. So I've got this helper function load MNIST shard, which is defined up here in MNIST utils. And this is how I actually load in my data. Obviously, for a real federation, you got real data files there. You're going to update this to say load a batch, and however you need to load in the files. Okay, so I've got my search directory, my code directory, my data, my logs, plan, requirements, and save. Next thing I need to do is initialize the plan. I won't go through the plan here. I'll just assume that this plan is what I want, which it is. We'll do other videos showing you how to change things in the plan, like changing the number of rounds to train and changing if you want a different set of tasks to run. But I'm going to take the plan that was given to me, and I'll just say plan initialize. The big thing here is the aggregator node needs to always be identified by its fully qualified domain name. This is probably the trickiest part of the setup is the aggregator. The collaborators can present themselves with whatever name they want as long as the aggregator knows you're going to be presenting yourself as beta 123 or something like that. But the aggregator needs to have its PKI certificate matching what its actual fully qualified domain name is. And that's actually a security feature in TLS gRPC that is just something that needs to happen. If it's not there, you might have something where your aggregator's running, it's listening, it's trying to connect to collaborators. Your collaborators are running, trying to connect, and they can never connect because the PKI certificate doesn't match the actual fully qualified domain name of the aggregator node. We try our best in the software to discover what your fully qualified domain name is. So if you just do fxplan initialize, it will try to figure that out. And it's usually something like you have to ask your system admin. Again, this is just on the aggregator node. But if you're not sure, other than etc hosts, you can do hostname -a, and it should show you the fully qualified domain name and a few other names for your node. So it's really like something dot something dot something dot something, and not the octets, not the numeric. So this one actually got it correct without me specifying it. It was able to discover it. It said, okay, here's what my fully qualified domain name is. So this is what my aggregator is going to start on. Here's my aggregator port that I'm going to start on. And then I'm going to have all certificates in the certificate folder, and then some more information this is all from the FL plan. So at this stage, I am set with the initialization of the plan. I'm going to skip over Docker. I'll do that for another time. This is probably the largest part of the setup. And again, PKI's certificates, normally should be set up using a professional CA, so you get a certificate that is uniquely yours. For simulation and for testing and for going through demos, we actually have a certificate authority that you can set up, and we usually just set it up on the aggregator. So I would say FX Workspace certify. Actually, let me show you the cert directory first. So there's nothing in the cert directory. And now if I set up FX Workspace certify, it will actually set up a certificate authority, CA, and a certificate chain in that directory. So now I've got a certificate authority that I control, and I'm going to create a certificate request from that authority. This happens to be on the exact same node for the aggregator. Again, if it can't discover it, what the fully qualified domain name is, you can put it right here. I think this one discovers, I think this node is set up that it can discover what the fully qualified domain name is. So I'll say create a certificate. So it grabbed the right fully qualified domain name, created a certificate. So now if I go to the search directory, I've got also a new server directory, and it has a certificate signing request and a key. So it can actually send the certificate signing request over to the certificate authority, but the certificate authority is already here. So I'm just going to say certify for the aggregator, and my certificate authority is here, so it knows where to find it. And it's going to say, I found a server ag with this hash. If this is coming from somewhere else, if your certificate authority server is somewhere other than your aggregator and you got this, you need to determine if, as a certificate authority, you're comfortable with signing the certificate and validating it. So you might call up the person who sent this certificate and say, did you really send this name certificate with this hash 8Fe803E9 and so forth? They say, yep, that was me. You can say, okay, that is your certificate. I'm going to approve that. And now if I go to the server, I've got now a certificate that has been signed by the certificate authority. And that is it for the PKI for the aggregator. So now we're set to actually export the workspace. So again, the workspace is this. And if I'm in that workspace, I can just say FX Workspace Export. It'll take the current workspace. It'll freeze the plan, give a hash to, what was frozen, so you can always verify that nothing has changed in the plan. It'll write a requirements file. If I've somehow installed something else in this virtual environment, it'll also grab anything I've manually installed. And it'll create this zip file for me, myfederation.zip. And this is how on step 3, I can now, there we go. So I've done step 1, I've installed everything, installed OpenFL. Step 2, I've created this workspace. And now step 3, and actually I've even created the aggregator, step 4 here, the CA. And now in step 3, I just need to transfer this to these other 2 nodes. So what I want to do here is, this is node, the collaborator node I'm calling alpha123 Intel. And I'm just going to use SCP to copy securely. So the aggregator node is, this is the shortcut to that. It's called my federation, and my federation.zip. I don't want to copy it here. And now it's over here. Okay. And I'm going to do the same thing on this one. So this is the second one, another collaborator I'm calling Beta 34 Gold. So I'm going to okay, so that's over here now. That. All right. And the good thing here to remember is, even though it looks like I'm copying all these files, again, this is owned by somebody who will copy their own files. This is owned by another person who will copy the workspace over. So that's really how it should end up working. Once I've got it over there, I can import it. So I've got FX running on both of these. Got FX installed because that was my first step. Install it everywhere. And FX installed here. So now I can do FX workspace import archive. And my archive is called myfederation.zip. And now it's going to install, it's going to use the requirements file to install anything that it needs to install in the environment. So MyBabel or Pillow or OpenCV, anything that you need to run your code. And then it says you may need to copy your PKI certificates to join the federation, which we will. All right, so my federation. So now I've got this new directory, my federation, where it unzipped everything. And I've got code, data, logs, plan. Again, there's nothing in the save directory because that'll come over from the collaborator at runtime, or from the aggregator at runtime. I've got the code that I need to run, which came over with the workspace. The data, I'm typically going to, in a real case, do a symbolic link to my own data, so it knows, my data loader knows to look under the data directory. I notice there's no cert directory here because we still have to create them. So do that. The same thing here. FX workspace import minus archive, and it's myfederation.zip. I do the same thing here. I got my federation and the same. Okay, so now I've imported it. What's great is I now have a way of getting certificates and getting certificates to be signed. So I can say, I want to create a certificate and I want to call myself Alpha123 Intel. Again, aggregators need to be the fully qualified domain name. Collaborators can be whatever name you pick. You can choose one. So I'm going to just choose this random name. And it's going to create a certificate with that identification. It says the certificate signing request, the CSR, should be typically sent to a certificate authority to sign it. Again, in a real case, you would be getting this from a competent or approved certificate authority. And again, the next thing it asks is, where's the data? In this case, it's for the MNIST. I showed you the data loader. It really is just going to be a 0 or a 1 for the shard. Okay, so now I've got a search directory, and it has the certificate signing request and the key that it's going to use as a collaborator. So now I want to now it's also given, sorry, it's also given me that certificate signing request is also packaged into a zip file called collaborator alpha123 Intel 2 aggregator certificate request. So now I can transfer that back and say this zip file goes back to the aggregator or wherever the certificate authority is. In this case, it happens to be in the aggregator. Okay, and now on my aggregator, I now have this request. So now back on the aggregator, I can certify. Well, it's actually, I keep saying aggregator, but the aggregator is my certificate authority. So I can certify that package, which has the certificate signing request. So it says, hey, I got a certificate signing request from somebody calling themselves collaborator alpha123 Intel, and it has this hash. Is that what you expect? So this collaborator, the person is going to call the certificate authority, in this case the aggregator, and say, hey, I sent this, or actually, I guess it should be the other way. The certificate authority should call them and say, did you send this? And can you confirm the hash And they'll say, oh, the hash is 5FF025. Okay, that's what I got. I'm going to sign it. Congratulations, you now have something that I signed. So I've got now something to send back to them. Ag to call alpha signed certificate. And I can send that one back. Okay, and now I've got that back. So let's take a look. My cert client still has these two. So I want to now import. Okay, so nothing in this, or just these certificate signing requests. So now all I have to do is I've got the aggregator to collaborator signed certificate, and I need to import it back into the collaborator. So import this aggregator. Now it's imported it. So if I go to my cert directory again, I now have the certificate as well as the CSR and the key. So this is what it's actually going to present to the Federation. Okay, so last one is I'm going to do the same procedure on my other collaborator. I'm going to create certificate request. And I think I called this one beta 34 gold. And same thing with this one, beta 34 gold. You want to create a certificate, you need to get it, certificate authority to sign it. Where's the data? Remember, for the MNIST thing, we're just doing shards in memory, so I just call it one, and my data loader knows how to handle that. Okay, so now I've got my collaborator beta 34 gold to aggregator. I can go back to sending that to my aggregator, or really my certificate authority. I want to send collaborator zip there. And, okay, and now back on here, I've got collaborator beta 34 gold request, which is here. So let's sign that. Certify collaborator beta for gold. And again, it says, hey, I got a certificate signing request. Give this person a call, ask them to verify their hash. Yes, it's D4, D3, CF46, and so forth. So I'm going to sign that, say you are who you say you are. And now I've got collaborators registered. So if I go to the plan.calls, let's cap that. So I've got collaborators alpha 1, 2, 3, and beta 34 gold have registered. And I can send now aggregator to collaborator back. This is the signed cert. So I'm going to send this there. Okay. And now I've got that back here. And now I can say, great, I've got it. And I need to import it. And let's just confirm cert client doesn't have, just has the CSR. So now when I import this, now it has the signed certificate from the certificate authority. Okay, so what have we done now? We have completed step 1, 2, 3, 4. We've got certificates everywhere. They're signed by the same certificate authority, so that everybody presumably trusts. And at the final step, we just need to actually run the workload. Fx aggregator start. So on the aggregator, I just say start running. It's going to read the FL plan. The FL plan now has authorized collaborators alpha 1, 2, 3 Intel and beta 34 gold. It had 10 rounds to train. It had these tasks, aggregated model validation and train and locally tuned. And right now it just has the aggregator's gRPC server is sitting there waiting for collaborators to connect. So I'll connect my first collaborator. Again, it presents its key, and it's presenting itself as alpha 123 Intel. It says, hi, I'm goes to the plan. Oh, sorry, collaborator start. Collaborator start. It presented that certificate, and now it has started. Um, so it actually finished the first round of training because it's a really small model. So it said, I got the following tasks from the aggregator. I did a round of validation. I did a round of training. Here's the loss, the first loss, and it did a round of accuracy. It's MNIST, so I started out with the initial weights were random, so it was basically random guessing, 0.097 accuracy, 0.91 accuracy after just a single round of training, and now it's waiting because it's here's the aggregator node saying, hey, I sent tasks to alpha 123 for round 0, and it sent me back information. And now I'm just waiting for the other collaborator. So fx collaborator start minus n and present the certificate 34 gold. Now it's going to present its certificate. And now the aggregator says, hey, great, I got something from beta 34 gold. This is still waiting for its task, but then collaborator beta 34 gold just actually sent back the result. So now round 1 can commence. So it's waiting for task, it's getting it. Put these 3 up at the same time. Okay, so we're at round 5. And so these are, again, aggregator, collaborator, alpha 123 Intel, collaborator beta 34 gold. These are 3 different nodes. And the only one that had to be properly named, meaning a fully qualified domain name with the certificate, was just the aggregator. We're finishing round 8, or starting round 8. Got the results back already. Round 9, we're going to go to 10 rounds. Finish round 10. And so aggregator is saying, okay, got to round 10, experiment has been completed, I'm cleaning up, sending signal to collaborator beta 34 gold and collaborator alpha to shut down. They got a shutdown command and the federation reached exiting, and the federation reached exiting. And what's great is if I want, now they've got this set up, if I want to rerun this, I can say fx aggregator start, collaborator start again, collaborator start again, and it will repeat the experiment. And then let's say that one of the nodes goes offline. So we're at round 1 now. Let's have it go offline at around, we're at round 2, I guess now. Okay. So let's say, whoops, this node went offline for some reason. So beta 34 gold sent its task back, but alpha did not. So now beta 34 gold is saying, great, I have finished, but I haven't gotten any new tasks. I'm just waiting for tasks. And aggregator is just saying, well, I've gotten stuff back for beta, but I gotta wait. So if alpha starts back up again, aggregator says, great, welcome back. Here are the tasks that you should be doing, and we're starting on round 3, and training continues. So I hope that was helpful. I know that was a long one, but I wanted to show you working through the entire federation for multi-node. Again, a great resource is to go through the online documentation here. If you want to see um, more information about, actually here's the starting the federation. You want to see more information about installing the software or particularly things like the plan settings, um, head on over to the documentation and we'll also do other videos. Till the next time, happy coding.